Okay, this is section 1.2. We're going to be talking about relations, functions, domain, range, graphs of relations, etc. Okay, so let's begin. The first thing to kind of, here we gotta get some vocabulary down first. The first thing I said we would need to talk about is a relation. So a relation, it's the more general thing here. Relations are the more general. Functions are a type of relation. Relations are more general than functions. Alright, so a relation is just a correspondence between a set called the domain and another set called the range, such that every member of the domain, so every element of the domain corresponds to at least one element of the range. Yeah? So you have two sets, one called the domain, one called the range, and each member of the domain corresponds to at least one member of the range. That's a relation. It's kind of very loosely based. It's just an association between two sets, one called the domain, one called the range. Sometimes the domain and the range are the same set. Okay, now what's a function? So a function is a type of relation. All functions are relations. The different, I guess what differentiates a function from a relation is that for a function, each member of the domain, so every member of the domain corresponds to exactly one member of the range. So that's the difference. Each member of the domain corresponds to only one member of the range. Whereas with relations, a member of the domain corresponds to at least one member of the range. So make sure that you see that difference. So in a function, every member of the domain, and that's kind of important, every member of the domain, every element of the domain corresponds to exactly one element of the range. And while you have these two sets, one of them is called the domain, the other one is called the range, they apply to both relations and functions. The domain is the set of all values. We'll get into domain and range here in a little bit. You can think of the domain as being all the x's and the range being all the y values. So the range is all the possible y values, the domain is all the possible x values. Now, when a relation happens to also be a function, we use a special type of notation. We replace the y's with f of x. This is just to kind of make the relation between the variable x and y a little bit more explicit. We know that y depends on my value of x. Remember, in the previous video, in the previous section, we said that we should treat x as the independent variable and y as the dependent variable. Let me jot that down over here. So x is independent. X is independent. Oops, let me erase this. And y, which I guess now we can also call f of x, is dependent. Okay, so let's see. Let's look at the first little example here. Here we have 4 examples of relations. These little diagrams are examples of relations. The element on the left is the domain. The set on the left is the domain. The set on the right is the range. These types of diagrams are called mapping diagrams, or these little diagrams sometimes you're called mapping diagrams, and what they are is just examples of relations. And right now what we want to know is determine if each of these 4 relations, which ones are functions and which ones are not. Okay, so let's see, I'll help you with one, and you'll pause the video after I help you with the first one, and then you'll try the next 3 on your own. So let me look at the first one, the one up here on the left. is this, so this is a relation, all of them are relations. The question is the relation a function? So let me think. So in order to be a function, we said, in order to be a function, what needs to happen is that a function, each member of the domain has to correspond to exactly one member of the range. So here I have an element of my domain, lizard, cat is another element of my domain, bird is another element of my domain, and they all correspond to exactly just one member of the range. So I am going to say that this relation right here is a function. This is a function. Now why? Because, well, because every element of my domain corresponds to exactly one element in the range. Okay, so that is my, so now pause the video and take a minute and see if you can answer whether or not the following three are functions. Okay, let's think about the next one. So this one over here to the right, the top right one. Is this a function? So each element of the domain is associated with one element in the range. It just so happens that lizard and cat got associated with the exact same element in the range, but both of them are associated with just one element in the range. So I am going to say that this thing is also a function. This is a function. All right, what about this example over here, this relation over here? Is this a function? Is this a function? So let's see, every element of the domain is taken up, it's being used, so that's good. And it should be the case that each element of the domain goes to exactly one element in the range. Well, right now I notice that cat is going to two different elements of the range. Cat is going to two distinct elements in the range. So this is not a function. That is one reason why this is not a function. This is definitely not a function. Why? Because this element of the domain cat got associated with two different elements of the range. And remember, our definition of a function is that each member of the domain corresponds to exactly one member of the range. What about the last relation? Is it a function? Well, let's see. Lizard is going to exactly one element of the range. Bird goes to exactly one element of the range. So far so good. That seems to be a function. But cat is not associated with anything. Yeah. So is that a function? Turns out that this is not a function. This is not a function. Why? Because, well, cat is not being associated with any elements of the range. There's an element in the domain that did not get associated with an element of the range. So this is also not a function. And we'll say here in this particular case that cat went to two distinct elements of the range. And so this is kind of the reason why this is not a function. Over here, the reason why this is not a function is that cat is not associated with an element of the range. That is why it's not a function. Okay. And whenever you have that a relation is a function, then we can use this function notation, f of x, g of x, h of x. So just remember that. Okay, let's think about the next example. Again, here is a little diagram, and it's a little mapping diagram. We have a couple of little mapping diagrams, and they want us to know whether or not these little relations are functions. And what can we say about the left one? What can we say about the left one? I mean, here, every element of the domain is being associated with exactly one element of the range. Sometimes they're associated with the same element of the range. Later on, we'll know that this is what's called not one-to-one, but right now, let's just think about functions. So I'm going to say that this guy right here is a function. Why? Because every element of the domain went and got associated with one element of the range. Sometimes the different elements of the domain go to the same element of the range. That's fine, as long as each element of the domain is associated with exactly one element in the range. So this guy's a function. What about this other relation here? Is it a function? I am going to say that it's not a function. Not a function. And the reason being is that this element of the domain 2 is being associated with two distinct elements of the range. Yeah, so the reason is because 2 is being associated with 3 and also with 10. So two distinct elements of the range. So this is not a function. So relations can be expressed in several forms. So far we've seen relations being expressed as these little mapping diagrams where little arrows are drawn between one set and the other. But relations can also be expressed graphically. If you think about the mapping diagrams, you could think of each association as an ordered pair. So for instance, I'm looking at this relation here, and I have that -6 goes to 36 and 6 goes to 36. So then I can sort of start thinking about an ordered pair, or points in the Cartesian plane. -3,9, etc. You get the idea. I can form ordered pairs from these associations of elements in the domain with elements in the range. And then what I could do is I could actually plot each one of those points. And then that gives a graphical representation of my relation, of my mapping diagram. Okay, so then we have several forms of expressing a relation, as mapping diagrams, as graphs. How do I determine if, so if I'm given a relation in a graphical form, how do I know if it's a function? That's the next thing. Okay, so it turns out that for graphs, and remember, graphs are just relations, because you can think of them as ordered pairs. So we can use what's called the vertical line test. Yeah, so if you're given a relation in the form of a graph, and you want to determine if the relation is a function, what you're going to have to do is you are going to use the vertical line test. And the way the vertical line test works is that you draw vertical lines through the graph. If a vertical line passes through a graph more than once, it is not a function. So if you draw a vertical line and the vertical line touches the graph at more than one point, it is not a function. So let's see. Let's think about the next little examples here. Let me look at this little graph here on the left. So this little graph, is it a function? So it's a relation. I mean, we can think of all of the ordered pairs that make up this little zigzaggy line and put them in a mapping diagram, and we could do that, but I mean that would be too tedious. So right now, if I happen to draw vertical lines anywhere through my graph, I will notice that those vertical lines touch my graph in only one point. So I am going to go ahead and conclude that this is a function. I'm going to say that it passes the vertical line test. It passes the vertical line test, so it is a function. Okay, What about the next graph? So let me think about this next graph right here. Is this a function? Well, let's see. Sorry about my computer. So let's see, is this a function right here? Let me draw some vertical lines. So there's a vertical line, and I notice that this vertical line happens to touch my graph in 3 points. So this is not a function. Not a function. What about the last one? What about this third one over here? Is it a function? If I draw a vertical line, does it touch my graph in more than 1 point? Well, I mean, if I draw a vertical line over here, it looks like a function. If I draw a vertical line over here, it looks like a function. What if I happen to draw a vertical line right on top of the y-axis? So it looks like my graph kind of gets closer and closer to the y-axis, but turns out that it will never cross the y-axis. So this is called asymptotic behavior. And since if my graph eventually crossed the y-axis somewhere up here and it also crossed the y-axis somewhere down there, then it would not be a function, but that's not going to happen. My graph is just going to get closer and closer and closer to the y-axis from the left and closer to the y-axis from the right, but the graph is never going to touch the y-axis. So I am going to conclude that this is a function. Okay, so now you have two ways of determining how to tell a relation from a function. If the relation is such that each element of the domain is associated with exactly one element of the range, then it's a function. Or if the graph passes the vertical line test, then it's a function. Okay, so what can you tell me about these two other relations here, these two other graphical relations? Are they functions or are they not? Let me begin with the easy one, the circle one. So let me think about the circle one. I'm going to draw a vertical line. There's my vertical line. It's not very vertical, but you get the idea. My vertical line touches the graph in 2 points. Yeah. So this is not a function. So this is definitely not a function. What about this other one right here? Is this a function? Well, let's see. Let's think about it. Is there, if I draw a vertical line somewhere, does it touch my graph in multiple points? So let's see. If I draw a vertical line, let's say over here. Oops. Let me draw it in black. Let's say I have this vertical line right there. Well, my vertical line only touched 1 point, so that's okay. If I draw, let's say, so I guess the points of interest are right here. What if I draw a vertical line right here? This vertical line happens to hit the x-axis at -2. And by the way, that line is called x equals -2. Imagine I have this vertical line, x equals -2. So, sorry, my lines are horrible, but I should just use a ruler. You get the idea. Imagine that I have a vertical line right here that hits the x-axis at -2. Does that line hit my graph at 2 points? And you might be thinking, yeah, I mean, I see that there are 2 points. I mean, my graph sort of breaks right there. This is a piecewise function. This is a piecewise graph. But the thing to notice is that you see there's an open circle and there's a closed circle. The open circle means that there's really actually not the graph doesn't touch that point. That's what the open circle is indicating, that the graph does not hit that point ever. Whereas up here, the closed circle says that it does hit that point. So if you think about it, if I was to draw a vertical line right here, at x equals -2, well, it's not going to touch in 2 places, because down here the point is not contained, up here it is contained. So it only touches once. Same thing is true for x equals 1. If you draw a vertical line through x equals 1, well, the vertical line will only hit up here at 5 because that's the point that's contained. It's not going to hit down here at -2 because the graph doesn't go through that point. So this guy turns out is a function. This guy is a function. This one's maybe a little tricky, but if you were to draw, again, a line through x equals 1, so if you drew a vertical line through x equals 1, that line will not touch my graph in 2 points, even though it looks like it does. It looks like it touches up here at 5 and at -2. But you see, the open circle at -2 is saying that my graph does not hit that point. So actually, if I draw a vertical line through x equals 1, my vertical line only hits this point up here at 5. So this is a function. This is a function. All right, let's see. So now we have 2 ways of determining if a relation is a function. One way is to see whether or not if every element of the domain is associated with exactly one element in the range. And the other way is to think about the vertical line test. Okay, so I guess a third way to give you a relation is as a set. This is a set, these curly brackets right here, they indicate a little set. It's a container, and the elements of the set are ordered pairs or points. Yeah, so this is a little set that contains 3 points, the point 9, -5, 9, and 2, 4. Yeah, that is a relation. And I guess the question is the relation a function? And also find the domain and the range. So let's think about this first part, part A. Is it a function? Do you think this is a function? I would say that this is not a function. This is definitely not a function. Why? Because 9 is associated with -5 and 5. And so that makes it not a function. If you were to graph these 3 points, what would happen is that you would have the following. So we can think about this graphically as well. Imagine that this is 9 right there. So then you have, and up here I have 5, and let's say down here I have -5. So I'm going to have the point 9, 5, which is this one. So I go to the right 9 and then up 5. And then I'm also going to have the point 9, -5. Well, I have to go 9 and then -5. And that's going to fail the vertical line test, because now I have a vertical line that hits these 2 points. Yeah, so it's not a function. Okay, so fine, it's not a function, but we can still talk about the domain. What's the domain? So the domain is going to be a set. It's going to be a set of numbers, and it's the set of all the inputs of all the x's. So I'm gonna open up a little set. This is set builder notation. So my little set is just right now these curly brackets. Think about the curly brackets as just being a little container. And then you have to tell me what's inside this container. And well, what's inside this container is all of the x coordinates of my points. That's my domain. So I guess in this case, my domain just consists of 9 and 2. Even though 9 shows up twice, well, I only counted once because I don't want to count it twice. It doesn't make any sense to count it twice. So this is a set. My domain is the set that contains the numbers 9 and 2. And it doesn't matter if you said, I mean, it's the same set as 2, 9. Yeah, it's the same thing. What about the range? What about the range for this relation? What is the range? Well, the range, again, is going to be a set. It's the set of all y values of my points. So -5, 5, and 4. Again, it doesn't matter in which order you listed them. You could have said 4 and 5, -5, or -5, 4, 5. It's the same set. Okay. So pause the video and try the next 2 on your own. determine if the relation is a function, state the domain in using set builder notation, and state the range also using set builder notation. Okay, so hopefully you try this on your own. Let's see. Let me think about the first one. So I'm not gonna, here I could make a little mapping diagram, but I am going to go ahead and just start looking at my elements of my domain, and the domain in this case is -2, 5, 0, 4, and there's no one element of the domain that goes to different elements in the range. So this is a function. This is a function. I'm going to say that the domain is the set -2, 5, 0, and 4. And the range for this function, the range is going to be 5, 7, 1, -2. What about the last one? Is it a function? I'm going to go ahead and say that it is a function. Even though all of the elements of my domain are going to the exact same element of the range, that's okay. The definition of a function is that each element of the domain has to be associated with only one element of the range. And so then that's true. Turns out that this is a function. The domain in this case is going to be -5, 0, 6, and the range in this particular little example is 3. It's just the set that contains the value 3. That's it. Okay, so hopefully you have this makes sense, this determining whether a relation is a function or not. Remember that if you're given the relation in a graphical form, you have the vertical line test at your disposal. All right. So let's kind of talk about the next example here. So now we have been given a function. So this thing turns out is a function. Its graph passes the vertical line test. Each element of the domain is associated with only one element in the range. So that's why we're using function notation, f of x. Remember, f of x is the same thing as y. We could interchange them, yeah? And you also gotta remember that x is the independent variable and y is the dependent variable. So think about you get to choose the value of x that you want, and depending on your choice, y becomes some value. Okay. So since this is a function, we're using function notation, and we gotta figure out what is f of 0. F of 0. So I'll help you with the first one, and then I'll let you try the other ones on your own. So let's see, f of 0. In order to figure out what f of 0 is, what I need to do is, well, replace all of my x's in my little function with 0. So that becomes 2 times 0 squared minus 0 plus 3. Okay. Well, 0 squared is just 0. 2 times 0 is 0, so 0 minus 0 plus 3. And well, turns out that that is 3. Yeah, it's as easy as that. I gotta replace all of my x's with, so you have this function notation, f of x. There's this little parentheses, and inside it, that's the input. That's the input for your function. So if your input is 0, you replace all of your x's with 0. If your input is a plus 1, you gotta replace all of your x's with a plus 1. Okay, so I'll give you a couple of minutes, pause the video, compute parts B, C, D, and E, and simplify them as much as you can. Okay, let's see. let's figure out part B. I gotta figure out what is f of negative 7. Yeah? So, well, what that means is replace all of your x's with negative 7. And since it's negative, actually doesn't matter what you're replacing your x's with. Just maybe put a parenthesis around. Think of x almost as a little container. And you gotta replace, you gotta put things in it. So let's see. So in this case, it's gonna be 2 times negative 7 squared minus negative 7 plus 3. So be careful here with signs, and also keep the order of operations, be aware of order of operations. The first thing I gotta do is square negative 7. Yeah? So negative 7 times negative 7, that's gonna become positive 49. So this becomes 2 times 49, and then this minus negative 7, in a sense that's a multiplication that's happening there. It's negative 1 times negative 1, well that becomes plus 7 plus 3. Okay, so 2 times 49, what is that? That's going to be what, 96? I think so. Let me, 2 times 49, so 98, sorry. 98 plus 7 plus 3. Yeah, so that's 98 plus 10. So 98 plus 10, that's going to be 108. Yeah? Okay. Now these other 3 remaining ones get a little weird. I think, I don't know, but you'll be the judge. So let's see. Let's try this f of a plus 5. Sorry, f of 5a. So I want to compute f of 5a. Okay, so everywhere where I have x, I'm going to replace x with 5a. I'm going to put parentheses around all of the 5a's though. So 2, and then 5a squared minus 5a plus 3. That's what it means. That's what f of 5a means. Okay, let me try to simplify this. I mean, technically at that point I'm done, that's it. But let me see if I can multiply this out a little bit further, or just simplify it. So this becomes 2, and then 5a squared becomes 25a squared minus 5a plus 3. And now if I multiply 2 times 25a squared, that's going to be 2 times 25, that's 50. 50a squared minus 5a plus 3. And now I have no idea what a is, and also, so I think that's as far as I can go, because I cannot combine a squares with just a. I mean, if this was 50a minus 5a, then yeah, I could conclude that that's 45a. But this is 50a squared, and this is just 5a, so they're not like terms. So I think that's as far as we can go. So for our first attempt, we had that's our answer, that's our answer there, and this is our answer here. Okay, let's try D. F of a minus 4. Okay, so anywhere where I have x's, I'm going to replace my x's with a minus 4. So that looks like this. 2 a minus 4 squared minus, I'm going to put parentheses, a minus 4 plus 3. Technically I'm done at that point, but I am actually going to kind of expand this out and try to write it as a polynomial in descending order. So let's see, let me show you what I mean here. So this is going to become 2. And now, what is a minus 4 squared? Let me remind you over here. A minus 4 squared means a minus 4 times a minus 4. This is a little bit of scratch work over here on the side. This is a little bit of scratch work that I'm doing. And then we gotta do what's called FOIL here. So kind of keep that in mind, because a minus 4 squared is not a squared minus 16. No, it's not. It's going to be a times a, and then a times negative 4 times a, and negative 4 times negative 4. That's how you multiply that out. So let's see, what do I get if I multiply this out? This would become a squared, and then minus 4a, that's minus 8a plus 16. Okay, so be careful. So this a minus 4 squared just became these three terms now. This becomes a squared minus 8a plus 16. Okay, so that took care of squaring that. Now let me distribute this negative. This negative needs to be distributed. In a sense, I need to apply it to that, and I need to apply it to that. So that's going to become minus a plus 4 plus 3. Okay, and now what I gotta do is I gotta distribute this 2. I gotta distribute this 2, multiply this 2 times a squared, multiply this 2 times negative 8a, multiply this 2 times 16, and then collect like terms. So this looks like this then, 2a squared minus 16a. Why 16a? Because 2 times 8 is 16, and then 2 times 16 is going to be 32, so plus 32 minus a, and then 4 plus 3, well, that's 7. Okay, so now let me collect like terms. So everything that's a squared needs to go with a squared. Everything that's a needs to go with a's. Everything that's just a number needs to go with a number. Yeah? So let's conclude this. It looks like I think my final form here is going to be 2a squared minus 17a. Why? Because negative 16a minus a, that's like saying negative 16 minus 1, that's negative 17. And then 32 plus 7, that's going to be 39. And I think that's as far as I can take that. That is as far as I can take that. Yeah? Okay. I'll let you do part E on your own. Just for the sake of time. So let's get into the next exercise here. A similar idea for the next exercise. We are given a function. The function is, it's called a rational function. It's a fraction, x minus 2 divided by x plus 3. And we gotta plug in some things into it. For instance, f of, let's do 2 of them. Let's just do 2 of them. So we have part A, B, and C. I am going to ask you to do parts B and C. You can do A on your own. Yeah? Let's do parts B and C. Pause the video, take a couple of minutes, try to do parts B and C. Okay, let's do part B. So I'm going to do f of negative 3. What that means is replace my x's with negative 3. Negative 3 minus 2 over negative 3 plus 3. Okay, so my numerator becomes negative 5 and my denominator becomes 0. And I'm sure you've heard at some point throughout your studies or in math that we cannot divide by 0. And if we do, we end up with this idea, this kind of mysterious thing called undefined. Yeah? Graphically, what would happen here is that if my x is equal to negative 3, you would have what's called a vertical asymptote. Yeah? So I guess for in our case, we just end up with this thing called undefined, and I guess that's as far as we can take it. All right. So let's see. Let's think about the next thing. Part C. You gotta figure out what is f of negative 3b. Okay, so we gotta replace our x's with negative 3b. So negative 3b minus 2 over negative 3b plus 3. Okay. If you're thinking, wait a minute, doesn't this negative 3 plus 3 also become 0? No, because this is negative 3 times b, and this is just 3. What can we do here? I don't think we can do much. That is pretty much it. This is it. I would say that this is our answer for this. So that is what f of negative 3b is in this particular case. Okay, so hopefully you're starting to feel comfortable with using, if you're not already comfortable, just with this function notation, f of x, g of x. And by the way, sometimes we can, you'll see g of x, h of x, n of x, whatever, it's just different functions, and you use different letters just to make sure that you don't use the same letter for different functions. All right, let's think about a little graphical situation here. So we were given a function in graphical form. This is our little graph right here, and it is a function. It passes the vertical line test. This function is called f of x. And based on the graph, they're asking us a few things. We're gonna have to approximate some of these things because it's kind of hard to give exact values, but we'll do our best. So let me begin with, like, for instance, with this. What is f of negative 4? How do I figure this out? Well, f of negative 4 is the y value that you get if your x is equal to negative 4. So again, f of negative 4 is the y value that you would get from the graph if your x happens to be negative 4. Okay, so then let me think. Let me first go to negative 4 on the x-axis. Negative 1, negative 2, negative 3, negative 4. What's the y value of my graph? Let's say it's right around there. And what is the y value there? Would you agree that that's 2? So I think I'm gonna go ahead and say that that is 2. Yeah, so first of all I had to go where x is equal to negative 4. 1, 2, 3, 4. And then I looked at the y value. What's the y value in my graph? It's about 2. So hopefully you get the idea here. Let's see. What is f of 0? So what this is saying is, what this is asking you is, what's the y value when your x is equal to 0? Okay, so let me go to where x is equal to 0. Where is x equal to 0? Right here at the origin. What's my y value? Well, it also looks to be, I would say, 0. Yeah? What about f of 3? What is f of 3? So what this is asking is, if my x is equal to 3, what's the y value? So 1, 2, 3. What's my y value? Well, yeah, that one's kind of hard to tell. We're going to have to kind of approximate that. So if my x is equal to 3, my y value seems to be something like, well, it's negative because it's underneath the x-axis, so negative 1.75, I'm going to say. Negative 1.75. Again, this is just an approximation. I'm not really sure, but somewhere close to that. So if my x is equal to negative 3, my y value is about negative 1.75. What about f of negative 5? If my x is all the way over here at negative 5, what's my y value? I would say, well, almost 0. It looks like it's 0. It looks like my graph goes back to 0. The y value is 0 at negative 5. Let's see. This other part. Find x when f of x is equal to 2. So now what they're saying here is, if the y is equal to 2, find the x's that correspond to that. Okay, well, let me see. Let me go to where x is equal to 2. Sorry. So find the x's when y equals 2. So y equals 2, 1, 2. Let me figure out the x's. So right there, y equals 2, and the x seems to be negative 4. So negative 4. But then notice, there's this other place right there. Right there, my graph, my y value is 2, and it looks like the x is what? it's a little bit less than 1, or rather negative 1, so a little bit bigger than negative 1. So something like negative 0.75. Do you agree with that? Look, if my x equals 4, negative 4, my y is 2. If my x is equal to negative 3/4, it looks like my y is also 2. Y being 2 right there. So I have two x's that go to the same y value. It's still a function, it's just not 1-to-1. And we'll talk about 1-to-1 further down the line. Now, what would you say, what are the x's that correspond to a y of 0? So this is my y-axis. Where is y equals 0? Well, right there. That's so it looks to me that I have two x's that correspond to y equals 0. Negative 5. So at negative 5, my y is equal to 0, and at 0. So hopefully this idea of figuring out x values or y values from a graph is okay, also using function notation. Okay, we're gonna stop this video right here. This is the first part, and we'll conclude this section in the next video. So I'll see you in the next video.